Antarctic krill are truly amazing animals just on their biomass, massive biomass, 160 to 500 million tonnes. And they've got this huge biomass because they're so good at doing their job, which is eating primary production, phytoplankton, and converting that into animal tissue, and then feeding the rest of the ecosystem. And they're truly quite remarkable in that they live for 5 to 7 years. They can shrink when they don't get enough food in the Antarctic winter. They're ready to hit that phytoplankton when it blooms in summer. And they're just really well adapted to this ecosystem. The boom and bust of the Antarctic is perfect for Antarctic krill.
And they're not a sedentary species, are they?
No, Antarctic krill are very active. They're pelagic, truly pelagic. They're not plankton. They don't just drift with the currents like smaller creatures will, because they actually swim after high zones of chlorophyll A. They're looking for that phytoplankton. And they're always swimming. They're obligate schoolers, so if you meet a bunch of krill during the daylight hours, they will be in a school, swimming, polarised together. And this is a way to avoid predation as well, because visual predators are confused by schools, just like a school of mullet will school up and it's hard to pick one individual out, the same for krill. It all turns against them though in the arms race with the great baleen whales, because a baleen whale will then come and take the entire school and then squeeze the water out. A blue whale has a 30 cubic metre mouth. That could be a metric tonne of krill in that 30 cubic metres if it met krill at peak density.
And how do they move vertically in the water column?
Yeah, so krill show a diurnal vertical migration, which means that each night they come up to the surface to feed. That's where most of their food is. It's the phytoplankton. That must be where the light is during the day for photosynthesis. So the krill just swim straight up through the water column and come up at night when no one can see them. The whole point being to avoid those visual predators. And we'll often catch krill by just drifting the net behind the Aurora australis at night at the surface, even when we can't see any krill on our echo sounders, because they're actually dispersed around the surface, frantically feeding on phytoplankton before diving down to the depths again before the daylight hours. We've been doing research here to look at the effects of carbon dioxide on the embryology of krill. We've found that if you expose krill eggs to high concentrations of carbon dioxide, they simply don't hatch. And the question then was exactly at what point does that occur? Where is the tipping point for Antarctic krill embryos? And it turns out that they start to show an effect once you get around 1,250 parts per million carbon dioxide. Current atmosphere is 400 parts per million. Okay, so that seems a long way off. But the current concentration of carbon dioxide at the hatching depth of krill is down around 550 now. And at the end of this century, the models are telling us that it's going to be around 1,500 parts per million. Now, once you get to 1,500 parts per million, we see a drop in hatch rate of around 20% from the experiments we've done in the lab. And if you go a little higher to 1,750 or 2,000, it's nearly nothing hatching. So these numbers seem high compared to what we're used to at the surface, but you've got to understand the oceanographic processes that are going on in the ocean to really see what's going to happen to these eggs, because these eggs are sinking from the surface down to maybe a kilometre deep before they hatch. So they're exposed to these conditions, not just the ones we have at the surface today. We've been looking at the effects of carbon dioxide, and now we're looking at carbon dioxide and temperature. We have carbon dioxide moving through these pipes here, aerating into columns of water. Each of these header tanks is at different temperatures, and then we're sending that water, now it's had adjusted carbon dioxide, down into these exposure tanks below. There are 3 replicated temperature tanks here. Each one contains 6 different concentrations of carbon dioxide, and each tank contains a tube which contains 8 jars of krill eggs. Each jar will have 20 krill eggs in it, and that will come from 1 female. So we can expose 3 different temperatures, 6 carbon dioxide concentrations, and really get to nail down the synergy of temperature and carbon dioxide, because it's likely to be much more than just an additive effect. Krill have a 2-year life cycle. So they're spawned every summer in the surface waters. The eggs are then sinking down into these waters that have higher carbon dioxide concentrations naturally, and now unnaturally are being taken even higher.
These pictures are the first ever photographic record of the entire life cycle of Antarctic krill. These were taken at the Australian Antarctic Division in Tasmania, the only place in the world where the development of live krill can be studied in a lab.
Down at 1,000 metres, they hatch into what's called a nauplius larvae, which then begins to swim back to the surface. And this is called a developmental ascent, because they're actually changing the shape of the larvae on the way up, going through these metamorphoses. And they go through up to 11 stages over the next 6 months. But from 3 weeks onwards, they've reached the surface, and then these larvae are really tightly associated with the sea ice. And what's really important is that when you get under that ice and have a look, you really do see these larvae tightly glued onto that ice, and they're feeding away under there. And it's really important to them. And we have seen evidence where we have a low ice year, we have low recruitment of larvae. It's essential for those larvae to have that ice. And understanding how that ice is going to be retreating around the Antarctic, how the changes in ice all tie into this whole story. So we don't just have one pressure on krill, we have this ocean acidification problem, we also have an ice retreat issue, and all of these things are going to act together to put pressure on krill.
Do we know enough about krill in winter and what happens under the ice?
Historically, all our work on krill was in summer, and that makes sense because that's when people go there if they want to come back without getting stuck. But recently we are pushing into the winter sea ice to do research. And this is multinational research. With other countries, we're participating in these winter cruises. And we are learning much more now about larvae. We're able to get samples of krill larvae during the winter to work on their physiology and to examine all sorts of aspects of them. But it's still an area that needs more research. We're still trying to answer some of those questions about where the larvae are, what they're feeding on, and also where exactly are the adults during winter. It's still very hard to nail down. They've been seen down at 3,500 metres down at the bottom. They've been seen under the ice, but exactly where the bulk of the population is, we don't know. There are still a lot of big unknowns about this animal.
What kind of capacity do krill have, do you think, to adapt to changing conditions like this?
Krill have a capacity to adapt to changes in their environment. They have to because they're here today. The one sort of definite thing about natural selection is extinction. If you can't cut it, you will go and something will replace you. The big problem for all of the life on our planet is that the changes that are happening to our planet now are just so much faster than what we've seen in the geological record. The geological record shows us numerous events of extinction, but they don't have a parallel to the rate of change that we're seeing now. It's just so fast. And the concern is that krill might not be able to adapt fast enough. These are not little organisms that swarm and multiply in a drop of water while you're out making a cup of tea. This is something that takes 2 years to get to sexual maturity from being an embryo, and might live for 5 to 7 years if it's not eaten by one of the predators. So this isn't something that can really turn over quickly and you can have selection happen very fast. It's something that needs time, and we might not give it that time.